Every telescope we build reveals a universe bigger than we imagined. But here's what astronomers won't tell you up front. We've barely scratched the surface. The observable universe stretches 93 billion light-years across, yet we've only mapped fragments of it. Everything we can see, every star, every galaxy makes up just 5% of what actually exists. The rest, hidden in plain sight. If you're enjoying this journey into the unknown, hit that subscribe button. We're just getting started. Prepare yourselves. The truth is stranger than you think. Light travels at 186,000 miles every second. You'd think that means we could see 13.8 billion light-years in any direction, since that's how old the universe is. But astronomers discovered something that breaks this simple math. The observable universe actually stretches 46 billion light-years from Earth in every direction. That creates a sphere 93 billion light-years wide. How does light from farther than 13.8 billion light-years reach us? The answer makes physicists uncomfortable. Space itself has been expanding. While ancient light traveled toward us, the universe stretched beneath it like a cosmic treadmill running in reverse. A galaxy that emitted light 13 billion years ago has since moved much farther away. We're seeing its past, but it now exists billions of light-years beyond where it appeared to be. This creates a strange truth confirmed by multiple observations. The edge of what we can observe keeps growing, but we'll never catch up to it. Every year, the observable universe expands by 1 light-year in radius. Every single year, new light reaches us from regions that were previously beyond our cosmic horizon. Think of it like standing in fog that slowly lifts. More landscape appears, but the fog bank itself keeps moving away from you. You see more, yet the total hidden area doesn't really shrink. The math gets wilder. The volume of space we can theoretically observe contains roughly 400 sextillion cubic light-years. Written out, that's a 4, followed by 23 zeros. Inside this volume, astronomers estimate between 200 billion and 2 trillion galaxies exist. Each galaxy contains billions or trillions of stars. Here's where the numbers become meaningless to human brains. If every star in the observable universe were a single grain of sand, you'd need more sand than exists on all Earth's beaches. Then multiply that by several hundred times. We're talking about 10,000 billion stars minimum, possibly much more. Yet, this incomprehensible number represents only what light has had time to reach us. Beyond our observable bubble, more universe exists. How much more? That's confirmed as unknown. Space might extend infinitely in all directions, or it might curve back on itself. Scientists genuinely don't know. What they do know makes the mystery deeper. Recent measurements suggest the actual universe measures at least 250 times larger than the observable portion. Some calculations push this to infinity. But even infinity has limits when we're trapped inside this cosmic bubble. What happens out there, beyond our horizon, might as well exist in another reality entirely. Astronomers spent decades cataloging everything they could detect. Stars, galaxies, gas clouds, planets, black holes, radiation. They added up all this matter and energy. The total came to roughly 5% of what the universe should contain according to gravitational measurements. 5%. Everything humans have ever seen, touched, or detected makes up 1/20th of reality. The realization hit the scientific community like a shockwave in the late 1990s. Observations of distant supernovae revealed the universe wasn't just expanding, it was accelerating. Something invisible was pushing space apart. Astronomers measured galaxy rotation speeds and found they spun too fast. Something unseen was holding them together with extra gravity. This wasn't measurement error. Multiple independent observations confirmed it. Galaxies behave as if they contain 10 times more mass than we can detect. Clusters of galaxies move as if bound by gravitational forces far stronger than visible matter could produce. The cosmic microwave background radiation shows ripples that only make sense if invisible matter dominated the early universe. Scientists invented names for what they couldn't see: dark matter and dark energy. Don't let the labels fool you. These aren't exotic theories waiting for confirmation. They're confirmed unknowns phenomena that definitely exist, but whose nature remains completely mysterious. Think about that distinction. We know with absolute certainty that something is there. We've measured its effects thousands of times. We just have zero idea what it actually is. Dark matter makes up roughly 27% of the universe. It has mass. It has gravity. It bends light through gravitational lensing, confirmed in countless observations. Galaxies swim through clouds of it. Some dark matter halos contain 100 times more mass than all the stars they surround. We've mapped its distribution across the cosmos using its gravitational fingerprints. But we've never touched it, never detected a single particle of it directly. It doesn't absorb light, doesn't emit light, doesn't interact with normal matter except through gravity. Imagine trying to study something that only makes itself known by pulling on things around it. Dark energy makes the situation worse. It accounts for 68% of everything. Its existence is confirmed through multiple lines of evidence, yet it seems to be a property of space itself. Empty space has energy. The more space expands, the more dark energy comes into existence. It's currently winning a war against gravity across cosmic scales. Here's what keeps physicists awake at night. We live in a universe where we can only directly observe less than 5% of what exists. The other 95% shapes. Everything determines how galaxies form, how the universe expands, how clusters hold together yet remains fundamentally invisible to us. The cosmos we think we know is just the visible foam on an ocean we can't fathom. Galaxies spin like cosmic pinwheels, but they shouldn't hold together. Stars on the outer edges move so fast that visible matter alone can't keep them bound. They should fly off into space like water droplets flung from a spinning wheel. They don't. Something invisible grips them. Astronomers first noticed this problem in the 1930s, when Fritz Zwicky studied the Coma cluster. Galaxies within it moved at such extreme speeds that the cluster should have torn itself apart billions of years ago. Zwicky calculated that the cluster needed 400 times more mass than he could see to generate enough gravity. He called it Dunkel materia, dark matter. Most scientists ignored him for 40 years. Then Vera Rubin measured rotation curves of spiral galaxies in the 1970s. Every single galaxy showed the same impossible pattern. Stars, far from the galactic center, moved just as fast as stars near the middle. The rotation curves stayed flat instead of dropping off. This violated everything physics predicted about orbital mechanics. Only one explanation fit the observations. Invisible matter formed massive halos around galaxies, extending far beyond the visible edges. These halos contained more mass than all the stars, gas, and dust combined. The ratio shocked everyone, roughly 6 times more dark matter than normal matter in a typical galaxy. Computer simulations confirmed this arrangement. Feed dark matter into models of galaxy formation, and you get structures that match what telescopes observe. Remove it, and galaxies don't form at all. The early universe would have remained a nearly uniform soup of gas. Dark matter's gravity created the scaffolding. Normal matter fell into the gravitational wells dark matter dug into space. The evidence became overwhelming. Gravitational lensing showed dark matter's distribution. When light from distant galaxies passes through massive clusters, the cluster's gravity bends that light. By measuring the distortion, astronomers map the dark matter. The maps reveal filaments, nodes, and voids a cosmic web of invisible material. The Bullet cluster provided smoking gun evidence in 2006. 2 galaxy clusters had collided and passed through each other. Normal matter, hot gas glowing in X-rays, stayed behind, slowed by friction. Dark matter passed right through, creating gravitational lensing effects far from the visible matter. This proved dark matter exists as actual substance, not just a fudge factor in equations. But what is it made of? That's the confirmed unknown mystery. Scientists have proposed dozens of candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos; primordial black holes; massive detectors; buried deep underground search for dark matter particles bumping into normal atoms. So far, nothing. Every experiment comes back empty, yet the gravitational evidence keeps mounting. Dark matter definitely exists. It outweighs normal matter 6-to-1 across the universe. It formed the structure we see. It holds galaxies together right now. We just can't figure out what it actually is. And that terrifies some physicists, because it suggests our understanding of matter itself might be fundamentally incomplete. In 1998, 2 teams of astronomers made a discovery that shouldn't be possible. They were studying Type Ia supernovae, exploding stars that always shine with nearly identical brightness. This makes them perfect cosmic measuring sticks. Find one, measure its apparent brightness, and you can calculate its distance. Both teams expected to find the universe's expansion slowing down. Gravity should gradually break cosmic expansion, right? Every mass in the universe pulls on every other mass. The data said otherwise. Distant supernovae appeared dimmer than predicted, meaning they were farther away than they should be. The universe hadn't been slowing down. It had been speeding up. Expansion was accelerating. Physicists checked the math dozens of times. The observations held up. Something was pushing space apart with ever-increasing strength. The discovery earned a Nobel Prize and created an existential crisis in cosmology. Scientists called it dark energy, though the name reveals nothing about its nature. Unlike dark matter, which clumps around galaxies, dark energy fills all of space uniformly. It exerts negative pressure, a repulsive force that counteracts gravity on cosmic scales. Here's the confirmed measurement. Dark energy makes up 68% of all energy in the universe. It's the dominant component of reality. Every cubic meter of empty space contains this mysterious energy, and as space expands, more dark energy comes into existence. The universe creates new energy from nothing as it grows. This violates human intuition about conservation of energy, but the math checks out under general relativity. Space itself can have energy as a property. Einstein actually predicted something like this with his cosmological constant, a value he later called his biggest blunder. Turns out he was right the first time. The effects are measurable and terrifying. Right now, dark energy is winning its war against gravity. Clusters of galaxies that are gravitationally bound will stay together, but everything beyond our local supercluster is accelerating away from us. Eventually, trillions of years from now, galaxies outside our gravitational neighborhood will move away faster than light can travel. Their light will never reach us. They'll fade from view one by one until observers in the distant future will see a mostly empty universe. The cosmic microwave background will be redshifted into invisibility. Evidence of the Big Bang itself will vanish. But here's what truly disturbs physicists. We have absolutely no idea what dark energy is. The leading theory suggests it's a property of space itself, vacuum energy. Empty space naturally contains energy even when nothing else is present. But when physicists calculate how much vacuum energy quantum mechanics predicts, they get a number 120 orders of magnitude too large. That's not a typo. The prediction is off by 1 followed by 120 zeros. It's the worst prediction in the history of physics. Something is catastrophically wrong with our understanding of reality. Yet the measurements keep coming in. Dark energy exists. It's accelerating cosmic expansion, and we're completely baffled about why. Robert Williams had an unusual kind of power in 1995. As director of the Space Telescope Science Institute, he controlled 10% of the Hubble Space Telescope's observation time. He could point humanity's most advanced eye at anything in the universe. He chose to aim it at nothing. Williams selected a tiny patch of sky in the constellation Ursa Major. The region appeared completely empty to ground-based telescopes. Just blackness. No bright stars. No obvious galaxies. Nothing of apparent interest. His colleagues thought he was wasting precious telescope time. Williams believed otherwise. He suspected that a long exposure might reveal faint, distant galaxies that no one had seen before. From December 18th to 28th, Hubble stared at this empty patch. 10 consecutive days. 342 separate exposures combined into one image. The result changed astronomy forever. The image revealed roughly 3,000 galaxies. Not stars, entire galaxies, each one containing billions of stars. They filled every corner of the frame, from bright spirals in the foreground to faint red smudges representing galaxies over 12 billion light-years away. Some were so distant their light had traveled for most of the universe's history. The Hubble Deep Field covered a patch of sky, equivalent to a tennis ball seen from 100 yards away. One tiny pinprick of the heavens. If you held a grain of sand at arm's length, it would cover roughly the same area. In this infinitesimal slice of nothing, 3,000 galaxies appeared. Do the math. The entire sky contains roughly 12 million such areas. If every patch contained 3,000 galaxies, the universe held tens of billions of galaxies minimum. Previous estimates had been way too conservative. But the real revelation came from the galaxies themselves. They showed incredible variety: spirals, ellipticals, irregular blobs, galaxies colliding, galaxies forming. Many looked nothing like modern galaxies, They appeared more chaotic, more active, stranger. Astronomers realized they were witnessing galaxy evolution across cosmic time. The farthest galaxies in the image existed when the universe was less than 1 billion years old. Their light had been traveling toward Earth for over 12 billion years. In that time, these distant galaxies had evolved, merged, and likely become massive elliptical galaxies by now. We were seeing their baby pictures. The scientific community produced over 900 papers based on this single image. It became one of the most analyzed photographs in astronomy. But Williams wasn't done. In 2004, Hubble went even deeper with the ultra-deep field 11 days of exposure, revealing nearly 10,000 galaxies. Then, in 2012, the extreme deep field pushed even farther, capturing galaxies 13.2 billion light-years away. Each deeper image revealed the same pattern. Point anywhere in the apparently empty sky, stare long enough, and thousands of galaxies appear. The universe is far more crowded than we imagined. Yet here's the haunting part. These deep fields together cover less than 1/10 millionth of the entire sky. We've seen incredible detail in these tiny patches, but they're needles in a cosmic haystack. What else is hiding in the darkness, waiting for us to look? Astronomers love to announce they've surveyed the universe. Press releases celebrate massive sky surveys with millions of galaxies. The numbers sound impressive until you examine what fraction of the sky was actually observed in detail. The Sloan Digital Sky Survey, one of the most comprehensive projects ever undertaken, mapped about 1/3 of the entire sky. That sounds substantial. But here's the catch. Even this massive survey only detected galaxies down to a certain brightness limit. Fainter galaxies, and there are billions of them, remained invisible. The Dark Energy Survey spent 6 years photographing the southern sky, 5,000 square degrees total. The team catalogued hundreds of millions of objects. Impressive work, but that represents roughly 1/8 of the sky. 7/8 remained untouched by their detailed observations. The Euclid Space Telescope, launched in 2023, aims to survey 15,000 square degrees. When complete, this will cover about 1/3 of the sky. It's the most ambitious mapping project ever attempted, yet 2/3 of the heavens will remain outside its field of view. Now consider depth versus coverage. The deeper you look, the smaller the area you can observe in a reasonable time. The James Webb Space Telescope can see incredibly distant galaxies, but its field of view is tiny. Imagine trying to survey an entire continent by looking through a straw. You'll see amazing detail in small patches, but massive areas go unexplored. The Cosmos Webb project recently compiled nearly 800,000 galaxies, reaching back 13.5 billion years. The research team celebrated it as the most comprehensive cosmic map ever created. The survey area? Less than 1 square degree of sky. The full sky contains roughly 41,000 square degrees. Do that division. The most comprehensive deep survey covers about 0.002% of the sky. We've achieved incredible depth in an area smaller than the apparent size of the full moon. Trade-offs are unavoidable with current technology. Telescope time is limited. Every hour spent staring at one patch means other regions go unobserved. Survey teams must choose: map wide areas with less detail, or probe deep into tiny regions. Most surveys choose wide coverage. They catalogue millions of nearby galaxies across large portions of sky. This reveals large-scale structure, how galaxies cluster into filaments and walls. But these surveys miss faint, distant galaxies that deep exposures would reveal. A handful of projects go deep instead, producing exquisite images of small fields. These reveal the distant universe in unprecedented detail, but their narrow view creates sampling problems. Maybe they happen to point at an unusually crowded region, or an unusually empty one. Small sample sizes introduce uncertainty. Here's what this means practically. Comprehensive maps of the nearby universe exist. Astronomers have catalogued galaxies within a few billion light-years fairly well. Beyond that distance, coverage becomes spotty. We have spectacular images of tiny areas mixed with vast unexplored regions. The total fraction of sky that's been deeply surveyed, meaning long exposures, revealing faint, distant galaxies, amounts to far less than 1%, probably closer to 0.1%. 99.9% of the deep universe remains unsurveyed territory. Literally, anything could be hiding there. and we'd have no idea. Our galaxy is sabotaging our view of the universe. The Milky Way stretches across the night sky as a luminous band of stars and gas. Beautiful to observe, but for astronomers trying to study distant galaxies, it creates a massive blind spot. This blind region is called the zone of avoidance. It covers roughly 20% of the sky, the areas where the Milky Way's disk lies between us and the deeper universe beyond. The problem is dust. Our galaxy contains vast clouds of cosmic dust, tiny particles of carbon, silicon, and other elements. These clouds scatter and absorb visible light. When astronomers try to observe distant galaxies through the zone of avoidance, the dust blocks their view like trying to see through fog. Some of the most interesting cosmic structures might be hiding there. The Great Attractor, a massive gravitational anomaly pulling our entire galaxy cluster, lies partially behind the zone of avoidance. Astronomers know something enormous exists there because they can measure its gravitational effects, but direct observation is difficult. In 2021, astronomers discovered the South Pole Wall, a massive structure containing hundreds of thousands of galaxies, stretching across 1.4 billion light-years. It had remained hidden partially because it lies in the zone of avoidance. Researchers only found it by using radio telescopes that can penetrate dust better than optical instruments. How many other structures remain hidden? The zone of avoidance could conceal entire superclusters. Major galaxy filaments might pass through this obscured region, connecting visible structures in ways we haven't mapped. We're essentially trying to understand cosmic geography while 20% of the map is covered by a giant smudge. Infrared and radio observations help. These wavelengths penetrate dust more effectively than visible light. Surveys at these frequencies have revealed previously hidden galaxies in the zone of avoidance. Thousands of galaxies have been discovered this way in recent decades, but infrared observations come with their own limitations. Telescopes sensitive to these wavelengths are harder to build and operate. The atmosphere blocks many infrared frequencies, requiring space-based observatories. Even the best infrared surveys don't match the depth and resolution of optical surveys in clearer parts of the sky. The 2MASS survey and the WISE satellite have catalogued millions of infrared sources through dusty regions. These projects revealed the Milky Way's zone isn't completely impenetrable, more like translucent. We can see through it with enough effort and the right instruments, but the view remains murky compared to clear sky areas. Consider what this means for understanding large-scale structure. Imagine trying to map ocean currents while 20% of the ocean is covered by thick fog. You can infer some things from the patterns you see in the clear areas. You can use indirect measurements to detect major flows beneath the fog, but you're definitely missing critical information. Galaxy surveys systematically avoid the zone of avoidance. Most large catalogues have gaps where the Milky Way obscures the view. These gaps create uncertainties in measurements of cosmic structure. Are the filaments and voids we observe representative of the whole universe? Or have we missed major features hiding behind our galaxy? Some researchers believe the zone of avoidance conceals structures that would change our understanding of the local universe's architecture. Others suspect nothing particularly unusual lurks there, just more of the same cosmic web we see elsewhere. Both groups agree on one thing: we won't know for certain until we develop better ways to pierce the veil. Our own galaxy ensures vast regions of the universe remain mysterious, possibly hiding surprises that would transform cosmology. In February 2025, astronomers announced they'd found something that shouldn't fit together. A superstructure so massive it challenged theoretical limits on how large cosmic structures could grow. They named it Quipu, after the ancient Incan recording system of knotted strings. The name fits. This cosmic giant resembles a vast filament with smaller strands branching off galaxy clusters linked together like knots on a cosmic thread. Quipu stretches 1.4 billion light-years from end to end. To put that in perspective, light traveling at 186,000 miles per second takes 1.4 billion years to cross it. The structure contains 68 galaxy clusters, each cluster holding hundreds or thousands of galaxies. Total mass: 200 quadrillion times our star's mass. The sheer scale violates expectations. According to standard cosmological models, the universe shouldn't have had enough time since the Big Bang for structures this large to form through gravitational collapse. Gravity works slowly on cosmic scales. Structures grow as matter clumps together, but there are limits. The theoretical limit calculated from the universe's age and expansion rate suggests maximum structure sizes around 1.2 billion light-years. Quipu exceeds this by 200 million light-years. Maybe that doesn't sound like much, but in cosmology, it's significant, like finding a human who's 10 feet tall when the theoretical maximum height is 8 feet. Quipu isn't alone. The same research team identified 4 other superstructures approaching similar sizes: the Shapley supercluster, the Serpens Corona Borealis superstructure, the Hercules supercluster, and the Sculptor Pegasus superstructure. Together, these 5 cosmic giants contain 45% of all galaxy clusters within their distance range, nearly half the matter in that region of space. These structures span the sky from southern to northern hemispheres. Quipu alone can be traced across multiple constellations from Pictor and Carina in the south, through Puppis, Lepus, Eridanus, Taurus, Triangulum, all the way to Perseus in the north. It dominates a massive swath of the observable universe. The discovery came from analyzing X-ray data from the Rosat satellite. Galaxy clusters contain hot gas that glows in X-rays. By mapping these X-ray bright clusters and calculating their distances using redshift measurements, researchers reconstructed the 3-dimensional structure of the local universe. When they plotted cluster positions, Quipu jumped out immediately. One researcher noted that the structure is readily noticeable by eye in a sky map of clusters without needing sophisticated detection algorithms. It's just sitting there, obvious once you know where to look, but finding it raises questions. If structures this large exist in the relatively nearby universe, Quipu lies between 425 and 815 million light-years away. What lurks in the more distant cosmos? Deeper surveys haven't reached the sensitivity needed to detect similar structures at greater distances. They might be out there, hidden by their extreme remoteness. Quipu also creates practical problems for cosmologists. These massive structures warp the cosmic microwave background radiation passing through them. They create gravitational distortions that affect measurements of the universe's expansion rate. Scientists must account for these effects when calculating fundamental cosmological parameters. The structure won't last forever, though. The universe's expansion will eventually pull it apart. Computer models suggest Quipu will fragment into several collapsing units as dark energy drives space apart. In the far future, what we now see as one connected structure will become separate, isolated clusters. For now, Quipu represents a physical entity deserving attention, a confirmed structure whose size pushes the boundaries of what physics says should exist. And it makes astronomers wonder what else might be hiding in the darkness, even larger and stranger. Between the filaments and clusters, something even stranger exists. Vast regions of space containing almost nothing. These cosmic voids stretch hundreds of millions of light-years across, with barely any galaxies inside them. The Boötes void was one of the first discovered. Astronomers found it in 1981 while surveying galaxy distributions. This void spans 330 million light-years in diameter. Inside it, they expected to find roughly 10,000 galaxies based on the universe's average density. They found 60 galaxies in a volume that should contain 10,000. The void is 99.4% empty compared to what it should be. These aren't just empty spaces where galaxies happen to be sparse. Voids have distinct edges, well-defined walls of galaxies surrounding nearly empty interiors. It's like the universe organized itself into foam. Galaxies cluster on thin sheets and filaments, surrounding enormous bubbles of mostly empty space. The largest known void, the giant void in the constellation Canes Venatici, measures roughly 1 billion light-years across. Imagine a sphere 1 billion light-years in diameter, containing just a handful of galaxies. Cross it at light speed, and the journey would take 1 billion years, during which you'd pass almost nothing. Voids aren't completely empty. They contain dark matter, just far less of it than average regions. Tenuous filaments of hydrogen gas thread through them. Occasional dwarf galaxies huddle in the darkness. But compared to the rest of the universe, voids are eerily vacant. Their existence reveals something fundamental about cosmic structure formation. In the early universe, tiny quantum fluctuations in density became magnified by expansion. Denser regions attracted more matter through gravity, becoming even denser. Less dense regions lost matter to their surroundings, becoming even emptier. Over billions of years, this process created the cosmic web, the largest structure pattern in the universe. Dense regions collapsed into galaxy clusters. These clusters connected along filaments. Between the filaments, voids expanded as their sparse matter drained toward denser regions. The process is still happening. Voids are growing. Their sparse matter continues migrating towards surrounding walls of galaxies. In the far future, voids will become even emptier as the last straggling galaxies either collapse into their centers or escape to the walls. Some voids show substructure, smaller voids within larger voids, creating a fractal-like pattern. The local void, roughly 150 million light-years across, sits near our Milky Way. We're positioned close to its edge, looking into a relatively empty region of space. Galaxies inside voids look different from those in denser regions. They tend to be bluer, younger, more actively forming stars. The isolation protects them from interactions and collisions that would trigger evolution. Void galaxies are cosmic hermits, evolving in slow motion compared to their crowded cousins in clusters. The Eridanus supervoid presents a different mystery. This massive void appears to create a cold spot in the cosmic microwave background radiation, a region where the ancient light from the Big Bang appears slightly cooler than surrounding areas. The void's presence might explain this anomaly, though the physics remains controversial. Mapping voids helps cosmologists test theories of structure formation. Computer simulations that include dark matter naturally produce cosmic webs with voids similar to those observed. Remove dark matter from the simulations, and the void structure doesn't form correctly. This provides indirect evidence that dark matter exists and drives structure formation. But voids also raise unsettling questions. Why did the universe organize itself this way? Could the pattern be different elsewhere in the unobservable universe? Are voids truly empty? Or do they contain dark matter structures we can't detect? Standing inside a void galaxy and looking at the night sky would be a strange experience. Far fewer galaxies would be visible. The universe would appear emptier, lonelier. Astronomers in such a location might develop very different ideas about cosmic structure. We're lucky, or perhaps not randomly placed, to live in a relatively dense region where the universe appears full of galaxies. But the voids remind us that most of space is exactly that, space. Emptiness dominates. Galaxy GNZ11 doesn't look like much in images. A faint reddish smudge, barely visible against the black background of space. But this tiny blob represents something extraordinary, the most distant confirmed galaxy in the observable universe. Its light traveled 13.4 billion years to reach us. When that light left GNZ11, the universe was only 400 million years old, 3% of its current age. We're seeing this galaxy as it existed in the cosmic dawn, shortly after the first stars ignited. The galaxy appears so distant that its light has been stretched by universal expansion. Originally emitted in ultraviolet wavelengths, it now reaches us in the infrared. The redshift value is 10.6, meaning the universe expanded by a factor of 11.6 since that light began its journey. Finding galaxies this distant requires extraordinary effort. They're incredibly faint. Their light has dimmed over billions of years of travel. Cosmic expansion has redshifted them out of visible wavelengths entirely. Only infrared telescopes can detect them, and even then, it requires long exposures. The James Webb Space Telescope, launched in 2021, is designed specifically to hunt these ancient galaxies. Its infrared vision can detect objects far beyond what Hubble can see. Early results from Webb have revealed galaxies that might be even more distant than GNZ11, though confirmation requires detailed spectroscopy. Some of these candidate galaxies appear surprisingly mature. They contain organized structures, disk shapes, hints of spiral arms that shouldn't exist so early in cosmic history. Standard models predict the first galaxies should look chaotic and irregular. Many of Webb's discoveries challenge these expectations. One gamma-ray burst, detected in 2009, came from even farther away, designated GRB 090423. This explosive event occurred 13.2 billion light-years from Earth. It lasted only 10 seconds, representing the death throes of a massive star when the universe was just 630 million years old. The burst happened, but we didn't see it until billions of years later. The light carried news of an event that occurred before our solar system existed, before the Milky Way had formed its current structure, before most stars in the universe had been born. Think about the strangeness of observing such distant objects. We're not seeing them as they are now. We're seeing their ancient past. GNZ11 as it currently exists is impossible to observe. The light showing its present state won't reach Earth for another 13 billion years. By then, our star will be dead, Earth will be gone, and no one will be here to see it. This creates a bizarre situation where the farthest objects we observe existed briefly in our past, but are completely inaccessible in our present. We can study their baby pictures, but never meet them as adults. Time and distance have separated us irrevocably. The observable universe has an edge, not a physical boundary, but a horizon beyond which we cannot see. This horizon exists because light from more distant regions hasn't had time to reach us yet. Every year, this horizon expands by 1 light year, revealing slightly more of the universe. But here's the twist. Dark energy complicates this. Objects beyond a certain distance are receding from us faster than light can travel. Their light will never reach us, no matter how long we wait. These regions are beyond our cosmic event horizon, permanently inaccessible. The farthest galaxies we can observe are approaching this limit, much more distant, and they cross into the zone of no return. Some galaxies that existed in the early universe have already passed beyond this horizon. We'll never see them. Their light is trapped in a region of space, expanding away from us superluminally. This means the observable universe isn't just limited by light speed and cosmic age. It's also limited by expansion. There's a maximum distance we'll ever be able to see, even with perfect telescopes and infinite patience. We're racing against cosmic expansion to observe the farthest galaxies before they disappear from view. Some already have. More will follow. Right now, galaxies are vanishing from the observable universe. Not dying or exploding, just accelerating beyond our cosmic horizon and winking out of detectability forever. The process happens slowly from our perspective. A galaxy that's barely visible now will fade over millions of years as cosmic expansion carries it away. Its light will redshift further and further into infrared, then microwave, then radio wavelengths. Eventually, it becomes so dim and redshifted that no telescope could detect it. Dark energy drives this process. As space expands, the expansion rate remains roughly constant per unit distance. This creates an exponential effect. Distant regions recede faster than nearby ones. Beyond a certain distance, currently about 15 billion light-years, regions of space recede faster than light can travel. Light from galaxies at that distance is fighting a losing battle. It travels toward us at light speed, but the space between us and them expands faster. The light makes progress, but the finish line keeps moving away faster than it can approach. It's like running on a treadmill that speeds up continuously. Here's what confirmed measurements tell us. Roughly 95% of the observable universe is already beyond our cosmic event horizon. We can see these regions because we're observing light emitted billions of years ago when they were closer, but we'll never see what's happening there now. That information is permanently inaccessible. Trillions of years in the future, assuming humans or their descendants still exist, the night sky will look very different. The Milky Way will have merged with Andromeda, forming a giant elliptical galaxy, but the rest of the universe will have disappeared. Nearby galaxies in our local cluster will remain visible. They're gravitationally bound, so expansion doesn't pull them apart. But everything beyond a few million light-years will have receded into invisibility. The cosmic microwave background will have redshifted beyond detection. Evidence of the Big Bang itself will vanish. Future cosmologists will face an extraordinary challenge. With no distant galaxies to observe, no cosmic background radiation to study, they'll have trouble figuring out the universe began in a Big Bang. Their observations will suggest they live in an island universe, one giant galaxy surrounded by eternal darkness. Everything we know about cosmology will be unverifiable in the far future. The evidence will have literally disappeared over the horizon. Future scientists might develop completely wrong theories about the universe because critical evidence has become inaccessible. This is already happening in reverse. There are galaxies beyond our current event horizon that we'll never observe. They existed in the early universe, emitted light toward us, but that light will never arrive. The space between us and them expanded too fast. We're permanently cut off from information about these regions. How many galaxies are we missing? Calculations suggest the actual universe contains far more galaxies than we can observe. If the universe is infinite, then the number of galaxies beyond our horizon is also infinite. We're observing an infinitesimal fraction of what exists. Even if the universe is finite but very large, we're missing most of it. Current estimates suggest the total universe is at least 250 times larger than the observable portion. That means for every galaxy we can see, there are at least 250 galaxies beyond our view. Some of these might harbor civilizations. Intelligent species might exist in regions of space we'll never observe. They could have radio telescopes pointed our direction right now, wondering if anyone's out there, but the signals they send will never reach us. Cosmic expansion has severed any possibility of contact. The expansion is accelerating. Dark energy is becoming more dominant over time. This means galaxies are disappearing from our view faster than new ones appear. The observable universe will eventually shrink not in size, but in content. More and more galaxies will cross the horizon and vanish. We live in a special time. The universe is old enough that we can study its history through distant observations, yet young enough that most of cosmic structure remains visible. Future observers won't have this luxury. The cosmos is hiding itself from us, one galaxy at a time. Nothing travels faster than light. This universal speed limit creates an expanding prison from which no information can escape. Light moves at exactly 186,282 miles per second in vacuum, not approximately exactly. This speed is built into the fabric of reality. Einstein's special relativity proved that accelerating any object with mass to light speed would require infinite energy. Photons reach this speed naturally because they have zero mass. This cosmic speed limit means information about distant events takes time to reach us. Light from our nearest star beyond our own takes over 4 years to arrive. Light from the Andromeda Galaxy, our nearest large galactic neighbor, travels for 2.5 million years before reaching Earth. We see Andromeda not as it is, but as it was 2.5 million years ago. Extend this logic to cosmic distances, and the problem becomes severe. The farthest objects we observe exist in our deep past. Their present state is completely unknown. They might have evolved dramatically, collided with other galaxies, or even been destroyed by some catastrophe. We won't learn about any of this for billions of years. But the speed limit creates an even worse problem when combined with cosmic expansion. Space itself can expand faster than light travels. This doesn't violate relativity because space isn't an object, it's the stage on which objects exist. The stage can grow at any rate. Currently, galaxies roughly 15 billion light-years away are receding from us at light speed. Beyond that distance, they recede faster than light. This distance is called the Hubble radius. It represents the boundary between regions we might someday observe and regions forever beyond our reach. Wait, though, if galaxies beyond 15 billion light-years recede faster than light, how can we see objects 13.4 billion light-years away? Shouldn't their light never reach us? The trick is that these objects were closer when they emitted the light we now observe. Their light was emitted when the universe was smaller, and those regions were within our Hubble radius. The light has been traveling toward us ever since, fighting against expansion but gradually making progress. However, light emitted today from galaxies beyond our cosmic event horizon will never reach us. The expansion carries them away faster than their light can approach. They've crossed a point of no return. The cosmic event horizon sits at roughly 15 billion light-years currently. This horizon is moving outward at light speed. Every second, it expands by 186,000 miles. Every year, it grows by 1 light-year in radius. New regions of space become theoretically observable as time passes. But here's where dark energy ruins everything. As space expands, more dark energy comes into existence, driving faster expansion. The acceleration means the cosmic event horizon isn't just moving outward, it's moving outward at an ever-decreasing rate. Eventually, it will stop growing entirely. When expansion becomes fast enough, the cosmic event horizon will reach a maximum radius and stay there. Any galaxy beyond that distance will remain permanently unobservable. The acceleration will carry them away so fast that no amount of waiting will allow their light to reach us. Calculations suggest this limiting horizon sits somewhere around 60 to 70 billion light-years from Earth. That's the absolute maximum distance we could ever observe, even with perfect instruments and infinite patience. Everything beyond that is permanently beyond our ken. The light speed limit also affects our ability to communicate across cosmic distances. Any signal we send to a distant galaxy travels at light speed. If that galaxy lies beyond our cosmic event horizon, our signal will never arrive. Space expands faster than the signal can travel. The recipient recedes into inaccessibility before the message reaches them. This creates a communication horizon separate from our observation horizon. We can observe galaxies in the distant past, but we can't send messages to them in the present. Any attempt to communicate fails because the expansion carries them beyond reach. We're trapped in an expanding bubble defined by light speed and cosmic expansion. The walls of this prison are growing, but not fast enough. More universe exists beyond our bubble than within it, and we have no way to access it. The speed limit isn't just a minor inconvenience. It's a fundamental barrier preventing us from observing most of reality. When astronomers measure a galaxy's distance, they're actually measuring how much its light has been stretched during its journey to Earth. This stretching, called redshift, turns the universe into a time machine. Light behaves as a wave. Like ocean waves, light waves have wavelength the distance between peaks. Blue light has short wavelengths around 450 nanometers. Red light has longer wavelengths around 700 nanometers. Different wavelengths produce different colors. When space expands, it stretches light waves traveling through it. A photon emitted in ultraviolet wavelengths might arrive at Earth as visible light or even infrared, depending on how much space expanded during the photon's journey. Astronomers see this as a shift toward the red end of the spectrum, hence redshift. The amount of stretching reveals distance. A galaxy with modest redshift is relatively nearby. Its light hasn't traveled long enough for significant stretching. A galaxy with extreme redshift is incredibly distant. Its light has been stretched enormously by expansion during a multi-billion-year journey. Redshift is quantified with the letter Z. A redshift of Z equals 1 means wavelengths have doubled. A redshift of Z equals 2 means wavelengths have tripled. The farthest confirmed galaxies have redshifts around 10 to 11, meaning their wavelengths have been stretched by a factor of 11 to 12. Here's where it becomes a time machine. Measuring redshift also measures time. The farther away a galaxy, the longer its light has traveled, and the farther back in time we're observing. Redshift and cosmic age are linked through the expansion history of the universe. A galaxy at redshift Z equals 1 appears as it existed roughly 6 billion years ago. Redshift Z equals 2 shows the universe at 3 billion years old. Redshift Z equals 6 reveals cosmic dawn at 900 million years after the Big Bang. Each observation peers into a specific era of cosmic history. Astronomers measure redshift using spectroscopy. Light from galaxies contains absorption and emission lines, specific wavelengths where elements absorb or emit light. These lines create a unique pattern, like a fingerprint. Every element produces characteristic lines at specific wavelengths. By comparing where these lines appear in a galaxy's spectrum to where they should appear in a lab, astronomers calculate how much the wavelengths have been stretched. If hydrogen's emission line normally appears at 434 nanometers but shows up at 868 nanometers in a galaxy's spectrum, that's a redshift of 1 the wavelength doubled. This technique works remarkably well. Modern spectrographs can measure redshifts to high precision. The Sloan Digital Sky Survey measured redshifts for millions of galaxies, mapping the three-dimensional structure of the universe across billions of light years. But redshift measurements come with caveats. Objects can also show redshift from their motion through space Doppler shift. A galaxy moving away from us will appear redshifted even without cosmic expansion. Nearby, galaxies show redshift contributions from both expansion and their peculiar velocities, their individual motions, relative to the average expansion. For distant galaxies, cosmological redshift dominates. Their recession velocities from expansion dwarf any local motion. But for nearby objects, separating the two effects requires careful analysis. Redshift also affects brightness measurements. As light is stretched to longer wavelengths, it loses energy. Photons arrive less energetic than when they were emitted. This makes distant galaxies appear dimmer than their distance alone would suggest. Astronomers must correct for this when calculating luminosities. The most extreme redshifts reveal the earliest galaxies. These objects appear faint and red, their light stretched from ultraviolet to infrared during the journey. Finding them requires infrared telescopes like James Webb. Hubble, optimized for visible light, largely missed these ancient systems. Each new redshift record represents pushing further into cosmic history. The current confirmed record sits around redshift 13, showing galaxies existing just 300 million years after the Big Bang. Webb might detect galaxies at redshift 15 or even 20, revealing an epoch when the first stars were just beginning to illuminate the darkness. Redshift has turned astronomy into archaeology. We don't just study where objects are, we study when they were. Every observation is a glimpse into history, preserved in light that's been traveling for eons. The universe's expansion has inadvertently created a vast archive of its own past, written in stretched wavelengths and encoded in ancient light. We're reading this archive, one redshift measurement at a time. There's a wall in time we cannot see past. Not because our telescopes aren't good enough, but because the universe itself becomes opaque beyond a certain point in its history. This barrier is the cosmic microwave background radiation released 380,000 years after the Big Bang. It represents the moment the universe cooled enough for atoms to form. Before this, the cosmos existed as an opaque plasma. In the beginning, the universe was so hot that matter existed as free electrons and protons flying independently. This plasma scattered light constantly. Photons couldn't travel far before bouncing off electrons. It was like trying to see through fog. The entire universe was opaque. As expansion cooled the cosmos, temperatures dropped below 3000 degrees Kelvin. At this critical temperature, electrons combined with protons to form neutral hydrogen atoms. This process is called recombination, though it's actually the first time atoms formed, making the name misleading. With electrons bound in atoms, they could no longer scatter light freely. The universe suddenly became transparent. Photons could travel unimpeded across space. The first light of the cosmos was released. These primordial photons have been traveling through space ever since. Over 13.8 billion years, cosmic expansion has stretched their wavelengths from visible light into microwaves. They arrive at Earth from every direction, creating a faint microwave glow filling the sky. This is the cosmic microwave background, detected in 1965 by Penzias and Wilson. Its temperature is now 2.7 degrees Kelvin, just above absolute zero. It represents the oldest light we can observe, a snapshot of the universe as it appeared 380,000 years after birth. The CMB forms an absolute barrier to optical observation. We cannot see anything earlier using light, because light couldn't travel freely before recombination. The universe before this point is hidden behind an opaque wall of plasma. However, the CMB itself contains information about even earlier times. Tiny temperature variations across the sky, 1 part in 100,000, represent density fluctuations in the primordial plasma. These fluctuations were seeded by quantum variations in the first fraction of a second after the Big Bang. Satellites like WMAP and Planck have mapped these variations with extraordinary precision. The patterns reveal fundamental properties of the universe: its age, composition, geometry, and expansion rate. The CMB has become cosmology's most important dataset, but it also defines our limit. Before recombination, the universe is opaque to electromagnetic radiation. We might detect earlier events through other means, gravitational waves, perhaps, or neutrinos that interact weakly with matter, but optical and radio telescopes hit a wall. Think about what this means. There's a surface in time beyond which we cannot observe using light. This surface, called the surface of last scattering, represents the farthest we can see with electromagnetic radiation. It exists at a redshift of roughly 1,100. The universe was 1,100 times smaller when this light was released. The CMB photons come from every direction, creating a spherical shell around us. This shell exists not in space, but in time. It represents a moment in history rather than a location. Every point we observe on the CMB sky shows a different region of the early universe, all observed at the same cosmic age. Observing the CMB is like standing in fog. We see the fog itself as a uniform glow, but we can't see through it to what lies beyond. The fog in this case is the opaque plasma of the early universe. Beyond it, earlier times remain hidden. Scientists have proposed ways to probe even earlier epochs. The cosmic neutrino background, if detected, would carry information from 1 second after the Big Bang. Primordial gravitational waves might preserve imprints from the first trillionth of a second. These signals could pierce the CMB barrier. So far, though, the cosmic microwave background remains our ultimate observational limit using electromagnetic radiation. It's a wall in time, not space. We can calculate what happened before it using physics, but we cannot directly observe those moments. The universe has hidden its earliest history behind this luminous fog. We see the fog with incredible clarity, but the darkness beyond it resists observation. Our view backward in time stops at the surface of last scattering, 380,000 years after the beginning. What happened before that? Theory suggests inflation, quark-gluon plasma, the formation of fundamental particles. But these remain beyond our direct view, hidden behind the oldest light in the universe. Astronomers face an impossible choice every time they design a survey. Go deep and see the faint, distant universe in exquisite detail, or go wide and map large areas with less depth. They cannot do both simultaneously with current technology. Telescope time is limited. Imagine you have 100 hours to observe the universe. You can point your telescope at one patch of sky for all 100 hours, revealing incredibly faint objects in that single region. Or you can split your time across 100 different patches, spending 1 hour on each, covering more area, but achieving less depth. The trade-off is fundamental. Collecting light takes time. Faint objects require long exposures. The longer you stare at a patch of sky, the more faint objects appear. But every hour spent staring at one location is an hour not spent observing somewhere else. Wide surveys map large fractions of the sky. The Sloan Digital Sky Survey covered 1/3 of the heavens. It catalogued hundreds of millions of galaxies. But its depth was limited. Most observations lasted only a few minutes per field. Faint, distant galaxies remained invisible. Deep surveys do the opposite. The Hubble Ultra Deep Field stared at one tiny patch for 11 days of total exposure time. It revealed nearly 10,000 galaxies in an area covering less than 1/10,000,000th of the sky. Incredible depth, negligible coverage. Both approaches have value. Wide surveys reveal large-scale structure. They show how galaxies cluster into filaments and voids across billions of light years. These patterns constrain cosmological models. Understanding the cosmic web requires mapping large volumes. Deep surveys reveal cosmic history. By detecting faint, distant galaxies, they show how the universe evolved. Early galaxies look different from modern ones. Star formation rates have changed. Galaxy collisions were more common in the past. Only deep observations reveal these distant objects. The ideal survey would be both wide and deep comprehensive coverage with exquisite sensitivity. But this requires impossible amounts of telescope time. To survey the entire sky to the depth of the ultra-deep field would take Hubble millions of years. New surveys try to find middle ground. The Dark Energy Survey covered 5,000 square degrees, substantial area while reaching moderate depth. It detected galaxies several billion light-years away, though not as distant as the deepest surveys. The Legacy Survey of Space and Time, planned for the Vera Rubin Observatory, will repeatedly image half the sky over 10 years. Each field receives multiple observations, building depth gradually while maintaining wide coverage. It's a compromise approach. But even Rubin won't match the depth of dedicated deep fields. Physics imposes limits. Light-gathering power depends on telescope size and exposure time. Larger telescopes collect more photons per second. Longer exposures accumulate more total photons. But there's only so much you can do. The James Webb Space Telescope represents extraordinary light-gathering power, a 6.5-meter mirror optimized for infrared, but its field of view is tiny. Surveying large areas would take centuries. Webb excels at deep observations of small regions, not wide mapping. Next-generation surveys must choose their priorities. The Nancy Grace Roman Space Telescope will balance depth and coverage better than previous missions. Its wide-field camera can image areas 100 times larger than Webb while maintaining decent sensitivity. But it still can't survey the entire sky deeply. This trade-off affects what we know about the universe. We have excellent maps of large-scale structure out to a few billion light-years. Beyond that distance, coverage becomes spotty. We have spectacular images of tiny deep fields reaching back 13 billion years, but these might not represent typical regions. What if the deep fields happen to point at unusually dense or unusually empty areas? Small sample sizes create uncertainty. Maybe the early universe was more uniform than deep fields suggest, or maybe it was more chaotic. Limited coverage makes it hard to say. Wide surveys might miss rare objects. If something interesting occurs in only one galaxy per billion, you need to survey billions of galaxies to find one. Narrow deep fields won't find such objects. Wide, shallow surveys might miss them if they're faint. The trade-off creates gaps in knowledge. We know the nearby universe fairly well and have detailed glimpses of the distant universe, but comprehensive mapping at all distances remains impossible. Astronomers must make hard choices. study a few fields deeply or many fields shallowly. Both approaches reveal important science, but both leave questions unanswered. Until technology improves dramatically, the depth versus coverage trade-off will continue limiting our view of the cosmos. We see fragments and samples, not the complete picture. In 1924, Edwin Hubble proved galaxies exist beyond the Milky Way. The universe suddenly became far larger than anyone had imagined. Hubble estimated perhaps millions of galaxies existed in the observable cosmos. He was off by a factor of 1 million or more. Early surveys counted galaxies by photographing the sky and examining the plates by hand. Astronomers literally counted dots, trying to distinguish fuzzy galaxies from stars. The Lick Observatory counted over 1 million galaxies in a survey completed in 1967. This seemed like an enormous number. Modern automated surveys have revised this figure upward repeatedly. The Hubble Deep Field in 1995 revealed that apparently empty patches of sky contained thousands of galaxies. Suddenly, estimates jumped to 100 billion galaxies in the observable universe. But that was just the beginning. Deeper surveys with better instruments kept finding more. The Hubble Ultra Deep Field in 2004 showed nearly 10,000 galaxies in a tiny patch. Galaxy counts continued rising. In 2016, a team analyzed all available deep field data and concluded the observable universe contains at least 2 trillion galaxies, not 200 billion, 2 trillion, 20 times previous estimates. Where did all these extra galaxies come from? They were always there, just too faint to detect. As telescopes improved, fainter galaxies became visible. Each advance in technology revealed more previously invisible systems. Many of these faint galaxies are dwarf galaxies, small systems containing millions to billions of stars, rather than hundreds of billions, individually unimpressive, but collectively numerous. For every large galaxy like the Milky Way, dozens or hundreds of dwarf galaxies exist. The 2 trillion estimate might still be too low. It counts only galaxies bright enough to detect with current technology. Even the deepest Hubble observations have detection limits. Fainter galaxies surely exist below this threshold. The James Webb Space Telescope is revealing more. Webb's infrared vision detects galaxies invisible to Hubble. Early Webb observations suggest there might be even more galaxies than 2 trillion. Some estimates now approach 10 trillion galaxies. But count gets complicated at high redshift. Very distant galaxies appear faint and small. Drawing the line between galaxy and proto-galaxy becomes arbitrary. Are we counting mature systems only, or including every clump of stars? Different surveys use different criteria, producing different counts. Some surveys count only galaxies above a certain mass threshold. Others include everything that resembles a gravitationally bound stellar system. Comparing counts across surveys requires careful attention to definitions. Here's the escalation in raw numbers. 1924, millions. 1960s, over 1 million catalogued. 1990s, 100 billion estimated. 2016, 2 trillion. 2025, possibly 10 trillion. Each decade brought upward revisions. The trend seems unlikely to stop. Better telescopes will reveal fainter galaxies. The true count might exceed 10 trillion. Some of these galaxies are massive ellipticals containing trillions of stars. Others are tiny dwarfs with barely 1 million stars. The size range spans factors of 1 million. Trying to count them all is like counting both elephants and ants and calling them equivalent. The number that matters for cosmology isn't the count, but the total stellar mass. How much matter is locked up in stars across all galaxies? This figure has changed less dramatically. Most of the mass resides in large galaxies, which were counted early. The newly discovered faint dwarfs add to the count without adding much mass. Still, the escalation is striking. We've gone from millions to potentially 10 trillion galaxies in 1 century. Each upward revision reminds us how little we've observed. And remember, these counts apply only to the observable universe. Beyond our cosmic horizon, more galaxies exist. If the universe is infinite, the total number of galaxies is also infinite. We're counting an infinitesimal fraction. Even within the observable universe, many galaxies remain undetected. They're too faint, too distant, or hidden behind dust and gas. Our current count of trillions represents a lower limit. The true number could be substantially higher. Every time astronomers think they've counted most galaxies, improved instruments reveal vast populations they missed. The pattern suggests we're still far from complete census. The universe is more crowded than we thought, and it keeps getting more crowded the harder we look. Our address in the universe just got longer. Astronomers discovered in 2014 that the Milky Way belongs to a supercluster 100 times larger than previously thought. For decades, scientists knew we lived in the Virgo supercluster, a collection of galaxy groups and clusters spanning roughly 100 million light-years. Our local group, containing the Milky Way and Andromeda, sits on the outskirts of this structure. But measuring galaxy motions revealed something unexpected. The Virgo supercluster wasn't a separate entity. It's actually part of a much larger structure defined by galaxy flows, streams of galaxies all moving toward a central gravitational basin. This megastructure is called Laniakea, Hawaiian for immeasurable heaven. It contains roughly 100,000 galaxies spread across 500 million light-years. Our previous address was just a neighborhood within a much larger city. Laniakea's discovery came from mapping galaxy velocities. Galaxies don't just participate in cosmic expansion, they also move through space based on local gravitational attraction. By subtracting the expansion velocity and examining only these peculiar velocities, astronomers mapped gravitational flow patterns. The patterns revealed basins of attraction regions, where galaxies flow toward common centers. Laniakea represents one such basin. All 100,000 galaxies within it are slowly falling toward a central region dominated by the Shapley supercluster. The boundary of Laniakea isn't defined by where galaxies stop, but by where their flows diverge. At the edge, galaxies start flowing toward different attractors. It's like a watershed. Rain falling on one side flows to one ocean. Rain on the other side flows elsewhere. This means superclusters can overlap and interpenetrate. Defining their boundaries requires choosing criteria. Using gravitational flow produces different boundaries than simply mapping galaxy density. Laniakea is large using the flow definition, but its mass remains concentrated in subclusters like Virgo and Shapley. The Great Attractor sits near Laniakea's center, a massive gravitational anomaly discovered in the 1970s. Our Milky Way and millions of other galaxies are being pulled toward it at 600 kilometers per second. The Great Attractor itself is being pulled toward the even more massive Shapley supercluster. These motions happen over cosmic timescales. We're falling toward the Great Attractor at 600 kilometers per second, which sounds fast but translates to only 20 light-years per 1,000 years. At this rate, we won't arrive for billions of years long after our stellar system has ceased to exist. Laniakea contains several prominent galaxy clusters. The Virgo cluster, with over 1,000 galaxies, dominates our local region. The Hydra and Centaurus clusters add more mass. The Shapley supercluster, containing thousands of galaxies, provides the ultimate gravitational anchor, but even Laniakea isn't the largest structure we're part of. Recent observations suggest Laniakea itself flows toward the Shapley attractor, which might be part of an even larger structure called the Pisces-Cetus supercluster complex. This vast filament stretches over 1 billion light-years. How far up does the hierarchy go? At some point, structures become so large, they're not gravitationally bound. They participate in cosmic expansion rather than collapsing together. Laniakea sits near this boundary. It's marginally bound, meaning expansion and gravity are nearly balanced. In the far future, dark energy will likely pull Laniakea apart. Regions currently part of one flow basin will separate as expansion accelerates. What we now see as a unified structure will fragment into isolated pieces. For now, though, Laniakea represents our cosmic neighborhood on the largest scales. It's the region of the universe we share a common fate with all 100,000 galaxies, slowly falling together toward a shared center of mass. Mapping Laniakea required measuring velocities for thousands of galaxies. The Cosmic Flows Project compiled these measurements, revealing the large-scale flow patterns. Future observations will refine the boundaries and identify even larger structures. But the discovery fundamentally changed our cosmic address. We're not just in the Milky Way, in the local group, in the Virgo supercluster. We're in Laniakea, a vast supercluster of superclusters, a basin containing 100,000 galaxies all flowing together through space. It's humbling. Our entire galaxy is one tiny part of 100,000 siblings, all caught in a gravitational dance spanning 500 million light-years. And this entire structure might itself be part of something even larger. Our place in the universe keeps getting smaller the more we learn. Massive objects bend space itself. Einstein predicted this in 1915, but seeing it happen took decades. When light from a distant galaxy passes near a massive cluster, the cluster's gravity warps space like a lens, distorting and magnifying the background galaxy. This creates spectacular illusions. A single galaxy can appear as multiple images scattered around a cluster. The galaxy's light takes different paths through warped space, arriving from different directions. Astronomers see the same object repeated 4, 5, or even a dozen times across the sky. Sometimes the geometry creates perfect circles called Einstein rings. The background galaxy, the lensing cluster, and Earth align so precisely that the galaxy's distorted image forms a complete ring around the cluster. These are rare but stunning when they occur. Gravitational lensing does more than create pretty pictures. It tricks our observations in subtle ways. The magnification makes distant galaxies appear brighter and larger than they actually are. Without correcting for this, astronomers would miscalculate distances and luminosities. The Hubble Space Telescope found some of the most distant galaxies by looking through massive cluster lenses. The cluster's gravity magnified faint background galaxies by factors of 10 or even 100, making them detectable when they'd normally be too dim to see. But lensing also hides information. The distortion scrambles the galaxy's true shape. Astronomers see a stretched, arc-shaped image rather than the galaxy's actual structure. Untangling the true appearance from the lensed image requires complex modeling. Weak lensing creates even subtler effects. Distant galaxies appear slightly elongated by foreground mass, but not enough to create obvious arcs or multiple images. The distortion is tiny, a few percent at most. Individual galaxies show barely detectable stretching. However, measuring weak lensing for thousands of galaxies reveals the invisible mass distribution. Dark matter doesn't emit light, but still bends space. By mapping how background galaxies are distorted, astronomers map dark matter across cosmic scales. This technique revealed the cosmic web. Dark matter forms vast filaments connecting galaxy clusters. Weak lensing traces these filaments, even where no visible matter exists. The observations match computer simulations remarkably well, confirming that dark matter drives large-scale structure formation. The bullet cluster provided the most direct evidence for dark matter through lensing. Two galaxy clusters collided and passed through each other. The hot gas visible in X-rays stayed behind, slowed by friction during the collision, but weak lensing revealed that most mass passed straight through without slowing. The lensing maps showed two distinct mass concentrations separated from the X-ray gas. This proved dark matter exists as actual substance rather than just a modification to gravity. Normal matter collided and slowed. Dark matter passed through collision-free, exactly as theory predicted. But lensing creates observational challenges. When surveying distant galaxies, some fraction are magnified by foreground lenses. This creates a selection bias. Lensed galaxies appear in surveys more often than unlensed ones because the magnification makes them brighter. Accounting for this requires statistical corrections. Survey teams must estimate what fraction of detected galaxies are magnified and by how much. Get this wrong, and you'll miscalculate galaxy abundances and luminosity functions. Strong lensing also plays tricks with time. Light taking different paths around a massive lens travels different distances. When a background galaxy's brightness changes, say, from a supernova explosion, we see the change at different times in different lensed images. Astronomers have observed this time delay effect in lensed quasars. One image brightens, then weeks or months later, another image of the same quasar brightens. The delay reveals the difference in light travel time between the paths. Measuring these delays helps constrain the expansion rate of the universe. The delay depends on the lens mass, geometry, and the Hubble constant. Observations of multiple lens systems can independently measure cosmic expansion. Gravity bends light, creating a cosmic funhouse mirror. Every massive object between us and distant galaxies potentially distorts our view. We're observing the universe through an array of gravitational lenses, each one warping space in its own way. Most of what we see is subtly distorted. We just don't always notice. Something massive is pulling the Milky Way through space at 600 kilometers per second. This gravitational monster, called the Great Attractor, sits roughly 250 million light-years away in the direction of the constellations Hydra and Centaurus. We can't see it clearly. The Great Attractor lies partially behind the zone of avoidance, obscured by our galaxy's dust and stars. Astronomers discovered it in the 1970s by measuring peculiar velocities of galaxies, their motions through space, beyond cosmic expansion. The pattern was unmistakable. Thousands of galaxies within hundreds of millions of light-years were all streaming toward the same region. Something enormous was pulling them. Calculations suggested the attractor contained the mass of tens of thousands of galaxies, concentrated in a relatively small volume. But direct observation proved difficult. Optical telescopes couldn't penetrate the Milky Way's obscuring dust. Astronomers resorted to other wavelengths. X-ray observations revealed hot gas from massive galaxy clusters. Infrared telescopes detected galaxies hidden by dust. Radio observations mapped hydrogen gas. These multi-wavelength studies revealed the Great Attractor isn't a single object, but a complex of massive galaxy clusters. The Norma cluster sits near the center, a rich cluster containing hundreds of galaxies. Surrounding it are several other massive clusters, all bound together by gravity. The total mass estimate approaches 1,000 trillion times our stellar mass. This enormous concentration of matter creates a gravitational well that dominates local space. Everything within a few hundred million light-years feels its pull, but the mystery deepened. Even the Great Attractor is being pulled by something more massive. The Shapley supercluster, sitting 500 million light-years away, contains even more mass. It's pulling the Great Attractor, which is pulling us. We're caught in a hierarchy of gravitational flows. These motions happen on timescales of billions of years. The Milky Way won't collide with the Great Attractor anytime soon. By the time we'd arrive, cosmic expansion driven by dark energy will have pulled the structure apart. We're falling towards something we'll never reach. The Great Attractor's location creates observational challenges. About 20% of the sky lies behind the Milky Way's disk from our perspective. Critical information about nearby large-scale structure remains hidden in this zone. The attractor sits squarely in the worst obscured region. Recent surveys using radio and infrared have mapped more of the hidden region. The HYPE survey Hydra Centaurus Pavo Indus revealed thousands of previously unknown galaxies behind the Milky Way. Many belong to clusters associated with the Great Attractor. These observations confirm that the Great Attractor contains several massive clusters rather than one supercluster. The Norma cluster anchors one side, the Centaurus cluster sits on the other. Between them lie smaller clusters and galaxy groups, all bound together. But mass estimates remain uncertain. Observations through the zone of avoidance are incomplete. Some clusters might remain undetected. The total mass could be higher than current estimates suggest. The Great Attractor also affects cosmological measurements. When measuring cosmic expansion using nearby galaxies, their peculiar velocities toward the attractor create systematic errors. Expansion appears different when looking toward the attractor versus away from it. Cosmologists must correct for these flows when calculating the Hubble constant. Ignoring local gravitational influences produces biased results. The Great Attractor's presence reminds us that the universe isn't expanding uniformly on small scales. Some galaxies within our local group will eventually escape the attractor's pull. Dark energy will drive expansion faster than the Great Attractor can pull things together. The structure represents a temporary configuration, massive now, but doomed to fragment as space expands. For now, though, it dominates our cosmic neighborhood. The Milky Way, Andromeda, and thousands of other galaxies are all being pulled toward this hidden mass concentration. We're passengers on a journey through space, driven by gravity from an object we can barely observe. The Great Attractor sits there in the zone of avoidance, pulling half the local universe toward it while remaining largely invisible, a gravitational giant hiding in plain sight behind our own galaxy's dust. Turn off visible light and turn on radio wavelengths, and the universe transforms into something almost unrecognizable. Objects that shine brilliantly in optical wavelengths vanish. Things invisible to normal telescopes suddenly dominate the sky. Radio waves are light waves, with wavelengths measuring millimeters to meters, thousands to millions of times longer than visible light. Our eyes can't detect them, but radio telescopes can. When astronomers first built radio telescopes in the 1930s, they discovered a completely different cosmos. Normal stars are nearly invisible in radio wavelengths. The optical night sky, filled with billions of stars, becomes mostly empty in radio. What appears instead? Exotic objects that barely show up in visible light. Radio galaxies become the dominant beacons. These systems harbor supermassive black holes, actively consuming matter. The infalling material doesn't fall straight in, it forms an accretion disk, heating to millions of degrees. Powerful magnetic fields channel some of this material into jets shooting outward at nearly light speed. These jets extend for hundreds of thousands, or even millions of light years. When the jet material slams into intergalactic gas, it creates enormous lobes that glow brilliantly in radio wavelengths. A single radio galaxy can span distances larger than dozens of Milky Ways placed end to end. In visible light, you might see a small, unremarkable galaxy. In radio, that same galaxy appears as a monster, with vast wings of emission stretching across the sky. The radio structure dwarfs the optical galaxy by factors of 100 or more. Pulsars, rapidly spinning neutron stars, emit powerful radio beams. They're virtually invisible in optical wavelengths, but shine like cosmic lighthouses in radio. Their regular pulses, ticking dozens to hundreds of times per second, can be detected across thousands of light years. The cosmic microwave background, invisible to our eyes, dominates the microwave portion of the radio spectrum. This ancient light fills the entire sky with faint radiation left over from the Big Bang. Radio telescopes designed to observe it see a universe bathed in primordial glow. Cold hydrogen gas, the raw material for star formation, emits radio waves at a specific frequency, 1420 MHz. This emission, called the 21 centimeter line, allows astronomers to map hydrogen throughout the universe. Vast reservoirs of gas, invisible in optical wavelengths, appear clearly in radio observations. Supernova remnants glow in radio. The expanding shells of gas from stellar explosions emit radio waves as they plow through interstellar medium. Some remnants are spectacular in radio but barely visible optically. Even our galaxy looks different. The Milky Way's spiral structure becomes more apparent in radio observations of hydrogen gas. Star-forming regions glow in radio from ionized gas. The galactic center, obscured by dust in visible light, reveals itself in radio and shows structures invisible to optical telescopes. Radio observations pierce through dust that blocks visible light. The zone of avoidance, that 20% of sky obscured by our galaxy, becomes partially transparent in radio. Astronomers can detect galaxies and clusters hidden behind the Milky Way's dust lanes. But radio astronomy has limitations. Radio wavelengths are much longer than visible light, which means radio telescopes need enormous size to achieve good resolution. A single radio dish produces fuzzy images. To see fine details, astronomers combine multiple telescopes into arrays. The Very Large Array in New Mexico links 27 dishes across 22 miles. Together, they achieve resolution rivaling optical telescopes. Even larger arrays like ALMA in Chile and the Event Horizon Telescope spanning the entire Earth push resolution further. Different wavelengths reveal different physics. Optical light traces stars and hot gas. Radio waves reveal cold gas, magnetic fields, and relativistic particles. Combining observations across wavelengths provides a complete picture. Some objects are radio loud, they emit more energy in radio than visible light. Quasars often fall in this category. Others are radio quiet, appearing bright optically but faint in radio. The radio universe isn't just a different view of the same cosmos. It reveals phenomena and structures that optical astronomy alone would never detect. Turn on radio eyes, and new universes appear: jets, pulsars, cold gas clouds, and the ancient microwave echo of creation itself. We're not just observing the universe in multiple wavelengths, we're observing multiple universes, each one revealing phenomena invisible to the others. The X-ray sky is violent. Objects that appear calm in visible light reveal their explosive nature when observed in X-rays. These high-energy photons come from matter heated to millions of degrees temperatures that would vaporize any known material instantly. Our atmosphere blocks X-rays completely, which is fortunate because cosmic X-rays would be deadly to life. But it also means X-ray astronomy requires space-based telescopes. The first X-ray observatory, Uhuru, launched in 1970. It revealed a universe far more energetic than visible light observations suggested. Black holes dominate the X-ray sky. When matter falls toward a black hole, gravitational energy converts to heat. The material spirals inward through an accretion disk, heating to temperatures exceeding 100 million degrees. At these temperatures, atoms emit X-rays. A supermassive black hole actively feeding can outshine its entire host galaxy in X-rays while appearing relatively faint in visible light. The X-ray emission comes from a tiny region near the black hole, sometimes smaller than our solar system, yet it radiates more energy than billions of stars. Neutron stars also shine in X-rays. These stellar corpses pack more mass than our star into a sphere just 12 miles across. Their surfaces reach millions of degrees. Some neutron stars in binary systems pull material from companion stars, creating X-ray sources so bright they were among the first cosmic X-ray sources discovered. Galaxy clusters revealed their true nature through X-rays. What appears in visible light as a scattered collection of galaxies becomes in X-rays a vast cloud of hot gas. This intergalactic medium, heated to tens of millions of degrees, contains more mass than all the galaxies combined. The gas fills the space between galaxies, glowing in X-rays but invisible to optical telescopes. The Chandra X-ray Observatory revealed extraordinary details. X-ray images of galaxy clusters show bubbles blown by supermassive black holes. The black holes at cluster centers inject enormous energy into surrounding gas, creating cavities hundreds of thousands of light years across. Supernova remnants create spectacular X-ray sources. The expanding debris from stellar explosions slams into surrounding gas at thousands of miles per second, creating shock waves that heat material to millions of degrees. Young remnants like Cas-A shine brilliantly in X-rays, revealing the violent physics of stellar death. The hot gas around galaxies came as a surprise. Our Milky Way is surrounded by a halo of gas at 1 million degrees. This corona remains invisible in visible light, but glows faintly in X-rays. Where this hot gas came from and how it stays hot remain active research questions. X-ray binary systems where a normal star orbits a black hole or neutron star create some of the brightest X-ray sources in galaxies. Material pulled from the normal star spirals toward the compact object, heating to X-ray, emitting temperatures. These systems flicker and flare, sometimes brightening by factors of thousands in hours. Active galactic nuclei appear modest in visible light, but dominate in X-rays. The supermassive black holes at galactic centers emit prodigious X-ray radiation when actively accreting matter. Surveys at X-ray wavelengths reveal millions of these active nuclei, many of which show minimal optical emission. The cosmic X-ray background, a diffuse glow of X-rays coming from all directions, puzzled astronomers for decades. Chandra and XMM Newton resolved this background into individual sources. Most are distant active galaxies. Collectively, millions of supermassive black holes across cosmic history created this X-ray fog. The deepest X-ray surveys, staring at small patches of sky for weeks, detect supermassive black holes across most of cosmic time. These observations show that black hole growth and galaxy formation are intimately connected. Nearly every massive galaxy harbors a supermassive black hole that was active in the past. X-ray observations reveal hidden populations. Some active galactic nuclei are so heavily obscured by dust that visible and even infrared light can't escape. But X-rays penetrate the dust, revealing black holes invisible at other wavelengths. Transient X-ray sources appear and disappear. Stellar flares, tidal disruption events, where stars are torn apart by black holes, and neutron star mergers all create temporary X-ray beacons. Monitoring the X-ray sky reveals a dynamic universe of violent events. The X-ray universe is hotter, more energetic, and more violent than the visible cosmos. It reveals the extreme physics happening around the most compact objects, black holes, neutron stars, and shock-heated gas. Without X-ray observations, we'd miss half the story of how matter behaves under the most extreme conditions the universe can create. Turn on X-ray vision, and the calm optical sky transforms into a scene of cosmic violence. The oldest galaxies in the universe are invisible to human eyes. Their light, emitted as ultraviolet and visible wavelengths billions of years ago, has been stretched by cosmic expansion into infrared. To see the earliest galaxies requires infrared vision. This is why the James Webb Space Telescope was built with infrared detectors rather than optical ones. Webb's mirror, covered in gold to enhance infrared reflection, collects light that left distant galaxies when the universe was just a few 100 million years old. Hubble Space Telescope, optimized for visible and ultraviolet light, could glimpse these ancient systems but not study them in detail. The galaxies appeared as faint red dots at the limit of detection. Webb sees them clearly, revealing structures and properties invisible to earlier telescopes. Infrared penetrates dust that blocks visible light. Star-forming regions are often shrouded in thick dust clouds. Visible light gets absorbed and scattered. Infrared passes through, allowing observations of stars forming inside molecular clouds. This capability alone revolutionizes our understanding of star formation. But infrared's biggest advantage is accessing high redshift galaxies. A galaxy at redshift 10 emits most of its light in ultraviolet wavelengths. By the time this light reaches Earth, expansion has stretched it into infrared. The farther away a galaxy, the more its light redshifts. The most distant galaxies only appear in infrared. The first Webb observations revealed galaxies that might exist at redshift 15 or higher. These systems existed just 200 million years after the Big Bang. Their light has been traveling for over 13.6 billion years, arriving at Earth as faint infrared photons. Some of these early galaxies look surprisingly mature. They show organized structures, disk shapes, even hints of spiral arms. Standard models predicted the first galaxies should appear chaotic, with irregular shapes and active mergers. Many of Webb's discoveries challenge these predictions. Dusty galaxies also reveal themselves in infrared. Some galaxies form stars so prodigiously that dust production outpaces supernova clearance. These systems become shrouded in their own dust, blocking visible light. They're nearly invisible to optical telescopes, but shine brilliantly in infrared. Sub-millimeter observations, even longer infrared wavelengths, detect the coldest dust. This traces star formation in the most obscured galaxies. Surveys at these wavelengths revealed vast populations of dusty starburst galaxies that optical surveys completely missed. The infrared sky looks different from the optical sky. Cool stars, red dwarfs, and brown dwarfs become prominent. These objects emit most of their light in infrared. Optical surveys barely detect them, but infrared observations reveal billions across the galaxy. Planets around other stars glow in infrared. While stars outshine planets in visible light, the contrast is much better in infrared. This makes infrared optimal for imaging exoplanets directly. Several planetary systems have been photographed using infrared adaptive optics. The center of our galaxy, heavily obscured by dust in visible wavelengths, appears clearly in infrared. Astronomers can track stars orbiting the supermassive black hole at the galactic center. These observations, impossible in visible light, proved a black hole exists there and measured its mass to high precision. Infrared observations reveal protoplanetary disks around young stars. These dusty disks, warmed by the central star, emit infrared radiation. Studying them shows how planetary systems form. Gaps in the disks mark where planets are currently forming. The Spitzer Space Telescope, operating from 2003 to 2020, surveyed large areas in infrared. It detected millions of galaxies, invisible to optical telescopes. Its deep surveys revealed star formation hidden by dust across cosmic history. The Wide Field Infrared Survey Explorer, or WISE, mapped the entire sky in infrared. It catalogued hundreds of millions of objects, dusty galaxies, cool stars, asteroids, comets. The survey revealed populations of objects that optical sky surveys missed entirely. Water, a key molecule for life, has absorption features in infrared. Observing these features reveals water in interstellar clouds, around young stars, and potentially in exoplanet atmospheres. Characterizing exoplanet atmospheres relies heavily on infrared spectroscopy, but infrared astronomy faces challenges. Earth's atmosphere glows in infrared from its own heat. Ground-based infrared telescopes must contend with this bright foreground. Space-based observatories avoid this problem, but require cooling to extremely low temperatures. Webb operates at -370 degrees Fahrenheit to minimize its own infrared glow. A massive sunshield blocks heat from the solar system, allowing the telescope to stay cold enough that its own heat doesn't overwhelm faint cosmic signals. The universe's oldest light hides in infrared. The earliest galaxies, the most obscured star formation, cool brown dwarfs, and exoplanet atmospheres all reveal themselves at these wavelengths. Without infrared vision, we'd miss the cosmic dawn entirely. The ancient universe only appears when we see in wavelengths our eyes cannot detect. The The observable universe contains roughly 2 trillion galaxies, spanning 93 billion light-years. But this might be just the tiniest fraction of what exists. If the universe is infinite, then everything we can observe represents exactly 0% of the total. Cosmologists don't know whether the universe is finite or infinite. Measurements suggest space is very flat, which is consistent with infinite extent, but flatness alone doesn't prove infinity. A very large, finite universe could also appear flat, just as Earth's surface appears flat locally, despite being curved globally. If space extends infinitely in all directions, then it contains infinite matter, infinite galaxies, infinite stars, and infinite planets. Our observable bubble sits within this infinity, like a grain of sand within infinite desert. Nothing we observe reveals whether infinite desert surrounds us. An infinite universe creates conceptual problems. Within infinity, every possible arrangement of matter that doesn't violate physics will occur somewhere, not just once, infinitely many times. Somewhere in an infinite cosmos, there might be an exact copy of Earth, complete with duplicates of every person who has ever lived. This sounds like science fiction, but it's a logical consequence of infinity, combined with finite building blocks. If you shuffle a finite deck of cards infinitely many times, every possible arrangement will appear infinitely often. The same principle applies to matter arranged in space. The probability of finding an exact duplicate Earth in any given random volume is essentially zero, but multiply zero probability by infinite volume, and the mathematics says duplicates must exist. An infinite universe doesn't just allow for copies, it requires them. Some cosmologists find this disturbing. Others argue it changes nothing practical. These duplicates, if they exist, lie beyond our cosmic horizon and always will. We can never observe them, visit them, or communicate with them. They might as well exist in separate universes. An infinite universe also means the question, how much have we observed, has a trivial answer: 0%. You can't observe a finite fraction of infinity. Every number divided by infinity equals 0. No matter how much our observable universe expands, we'll never observe more than 0% of an infinite cosmos. This makes certain cosmological questions meaningless. What's the average density of the universe? Has no answer if the universe is infinite and non-uniform. You can calculate average density within the observable region, but extrapolating to infinity creates problems. Inflation theory, which describes the universe's early rapid expansion, generically predicts an infinite universe. If inflation occurred, space likely expanded to infinite size during the inflationary epoch. The theory doesn't require infinity, but most versions produce it naturally. Observational tests can potentially distinguish between finite and infinite. Measuring space's curvature with high precision could reveal positive curvature, which would prove the universe is finite. So far, measurements show flatness within error bars, leaving both possibilities open. A positively curved universe would loop back on itself like a sphere's surface. Light traveling far enough in one direction would eventually return from the opposite direction. We could theoretically see multiple images of the same galaxy in different parts of the sky. Searches for such repeating patterns have found nothing. The cosmic microwave background provides the most precise curvature measurements. The pattern of temperature fluctuations depends on space's geometry. Current data are consistent with flatness, suggesting either infinite extent or a finite universe much larger than the observable region. If the universe is finite but very large, say 1,000 times the observable universe, we'd have no way to tell from inside our cosmic bubble. The curvature would be too slight to detect. We'd observe apparent flatness, even though space actually curves. Philosophers debate whether infinity truly exists in nature or is just a mathematical abstraction. Physics equations contain infinities, but maybe these represent limits of the theory rather than physical reality. Perhaps something prevents true infinity from manifesting in the actual universe. For practical astronomy, the question matters little. We can only observe the observable universe regardless of what lies beyond. Our theories must work within this bubble, whether infinite or finite universe surrounds it. But intellectually, the question profoundly affects how we think about existence. Are we one planet in one galaxy, in one observable bubble within infinity? Or are we a measurable fraction of a large but finite cosmos? The answer determines whether how much we've observed is 0% or some tiny but non-zero fraction. Until observations reveal space's true geometry, Both possibilities remain open. We might live in an island universe or within infinite expanse. The cosmos isn't telling us which. Technology improves constantly. Telescopes get bigger, detectors become more sensitive, and image processing algorithms grow more sophisticated. But fundamental physics imposes limits that no amount of engineering can overcome. Light gathering power depends on mirror size. Larger mirrors collect more photons per second from faint objects. The James Webb Space Telescope's 6.5-meter mirror collects more light than Hubble's 2.4-meter mirror. Future telescopes might reach 30 meters or even larger. But building such monsters presents enormous challenges. The mirror must maintain its shape to nanometer precision. Temperature variations, vibrations, and gravity all distort the surface. Keeping a 30-meter mirror stable enough for high-resolution imaging requires extraordinary engineering. Ground-based telescopes face atmospheric turbulence. Air currents blur starlight, limiting resolution. Adaptive optics partially correct this by using deformable mirrors that adjust thousands of times per second. But perfection is impossible. Space telescopes avoid atmosphere entirely, achieving resolution limited only by mirror size and light's wavelength. Diffraction creates ultimate resolution limits. Light waves bend around edges, creating diffraction patterns. Smaller wavelengths diffract less, allowing better resolution. This is why ultraviolet telescopes achieve better resolution than infrared telescopes of the